Now, to determine the equilibrium concentrations of a reaction from the equilibrium constant, we got to know Kc. Okay, we got to know the equilibrium constant value itself. So we're going to set up an ice table. Okay, we're going to make the changes in terms of X. Again, always losing our reactants and gaining our products. We're going to substitute into the equilibrium constant expression the equilibrium values from the ice table in terms of X. Then we're going to solve the equilibrium constant expression for X, and then we're going to be able to determine what the equilibrium concentrations are. We kind of did that in those first couple slides that I showed you with the Haber process, right? We determined what X was, and then we were able to determine the equilibrium concentrations. So let's try an example. I want to know, what is the molarity of all the compounds from a mixture which is initially contains 1 mole each of carbon monoxide, carbon, and water in a 50-liter container at 1,000 degrees Celsius when it reaches equilibrium? Kc for this reaction was already determined to be 0.58 at this temperature. Okay, so our first step is going to be to set up an ice table. Those ice tables are going to contain the initial concentration. So I need to first find out what are the initial concentrations of my reactants. So both of them were 1 mole and then divided by 50 liters because we want to get that in terms of molarity. So that's going to be 0.02 molar for the carbon monoxide and 0.02 molar for the water vapor. And again, we always assume that we're starting off with a clean reaction vessel. So unless otherwise stated, there's always going to be 0 products. Now, later on, we're going to find out that we might start with both reactants and products in a reaction vessel. But if it's not stated, we assume we started off with a clean reaction vessel and that there's no products in it. So our next step then is to set up an ice table. Okay, so our initial concentrations were the 0.02 CO, the 0.02 H2O, and 0 of both the CO2 and the H2. Okay. Our change, again, we're going to lose our reactants. So minus 1x for the CO, minus 1x for the H2O, plus 1x, we're going to gain our product. So plus 1x for the CO2, and plus 1x for the H2. At equilibrium, we just add our initial and change. So 0.02 minus x, 0.02 minus x, 0 plus x is just x, and 0 plus x is just x. Now we can plug this into our equilibrium constant expression, which is going to be K is equal to the K is equal to the concentration of CO raised to the first times the concentration of H raised to the first, divided by the concentration of CO raised to the first, divided by the concentration of H2O raised to the first. Okay. Now, I already know the equilibrium constant. It was given to us in the question. I think it was 0.58. And then here are the equilibrium concentrations that we're going to plug into our values here. Okay. So there's our 0.58. Here was our CO2 at X, our H2 at X. So that's X times X. Then our CO was 0.02 minus X, and the H2O was 0.02 minus X. Now, you should be able to recognize, you should be able to do fairly simple algebra here, right? So this is basically X squared over 0.02 minus X squared. So to make this easy, so I don't have to solve the quadratic formula, which by the way, you're gonna have to, okay? But this time I don't have to, because I could simply take the square root of both sides. And if I take the square root of x squared, that's just x. And if I take the square root of 0.02 minus x squared, it's just 0.02 minus x. So I'll just take the square root of both sides. I also got to take the square root of 0.58, which ends up being 0.76. Now I'll multiply both sides by 0.02, so it'll cancel over here and it'll come onto this side, okay? I'll take 0.76 times 0.02 and then minus 0.76 times x, which is just 0.76x, and that all equals x. Now I'll add 0.76x to both sides, and so that gives me 1.76x. I'll divide both sides by 1.76x, And that tells me that X is then 0.0086. Now that I have X, I can plug that in to the equilibrium concentrations in the ICE table and find out the equilibrium concentrations of both my reactants and products. So for CO, it was 0.02 minus 0.0086. So the CO is 0.0114 molar. Same thing's going to be true for the water. X is just equal to the concentration of CO2 and H2. So there now is my equilibrium concentrations. So all I need to know are the initial concentrations and the value of K, and I can calculate the equilibrium concentrations of any chemical reaction. Any questions on any of that good stuff?
When can we do the small number approximation on that? Just so we don't have to do any math.
We will do that in coming chapters. That works when you have very small values of K. It does not work when you don't have very small values of K. So in this case, we have 0.58. That's a large K. That approximation would not work for this problem. Again, I know some of you may, most of you probably don't even know what I'm talking about. We will get to that into the next chapter, okay? In this chapter, you have no choice but to solve the quadratic formula because the approximation method is not going to work, okay? So we'll talk about when it works and when it doesn't work. We'll actually have a little equation to determine when and we can use it and when we can't use it. Okay, so let's try another example. So again, here we have a chemical reaction between hydrogen and iodine to form hydrogen iodide. We have starting concentrations. We have 1 mole of H2 and 2 moles of I2. They're both in a 1 liter vessel. So that means the molarities are just 1 molar and 2 molar, right? 1 divided by 1 is 1, 2 divided by 1 is 2. So there's our initial concentrations, 1 molar H2 and 2 molar I2. And we want to know how many moles per liter. So we want to know the molar concentration of each of the substances once it reaches equilibrium at a temperature of 458 degrees Celsius. K at this temperature is 49.7. Okay, so we're going to go through and do the exact same thing again. We got to set up our ICE table, okay? Get our initial concentrations, easy in this case. Again, assuming that our products are 0, we got a clean reaction vessel to start with. Our initial concentrations enter the 1 molar H2, 2 molar I2, and 0 molar HI. Again, we always assume that the reaction proceeds in a forward direction, so we're always going to lose our reactants. So minus 1x for the H2, minus 1x for the I2, and we're going to gain our product, so plus 2x for the HI. Equilibrium, we just add the initial and change, so that's going to be 1 minus x, 2 minus x, and this will be 2x. Now we plug it into the equilibrium concentration, so we have H2 squared divided by H2 divided by I2. Now we can plug in our equilibrium concentrations and our value for K. This time though, these are not the same, so it's not this quantity squared, so we just can't take the square root. Now you have no choice but to do the quadratic formula. Okay, to use the quadratic formula though, we got to set this up in a form, a very specific form. Okay, so the form, it looks like this. I have ax squared plus bx is plus c is equal to 0. So it has to be in this form. When it's in this form, you now know what a, b, and c are, and they get plugged into the quadratic formula. So it's negative b, and then plus or minus. In other words, there's 2 answers to this. So it's plus or minus the square root of b squared minus 4ac, the whole thing divided by 2a. You got to do your homework. You got to be proficient at using this equation because you're going to use it not all the time, but you're going to use it often enough. And you're definitely going to be using it on exams. Okay? So you got to be proficient to know how to rearrange your equation the way it's supposed to, and then be able to plug it into your calculator correctly. Okay? Okay, so we need to get our equation, our equilibrium constant expression in this form here. So I'm going to let you do that. Okay, you should be able to do that. So basically all we did is we took this here, right? Multiplied this out and then multiplied the denominator over to here and then subtracted or added to both. And that gave us this equation right here. So okay, Kayla, what is the value of A?
You said Kayla?
Yep.
Okay, 45.7.
What is the value of B?
Negative 149.1.
Exactly, negative 149.1. And C? It's 99.4.
0.4.
Yep, okay. So everybody sees that, right? This is plus and plus. So if there's a negative appearing in there, that means that's part of the value. That's B is negative 149.1. So you're going to plug those values in for B, A, and C, and you're going to end up with two values, right? Because you have, again, you have a plus, and then you got to do it again where it becomes a minus, and you end up with the two values. Now, I know that a lot of your calculators, you just type in the A, B, and C, and it spits it out for you. But I would suggest that you type it into your calculator and make sure that you could do it that way as well. You should be able to know how to do this kind of stuff. Okay, so we got two values of X, 2.33 and 0.93. X can be positive or negative. Okay, it can be positive or negative. If X is positive, it means the reaction was going in the forward direction. And if X is negative, it means your reaction's going in the reverse, right? If X was negative, it means the HI was decomposing into H2 and I2. However, the concentrations always have to be positive. You can't have a negative concentration, okay? So we got to pick, there's only one X value that's going to work. And we got to pick the X value that's going to give us a positive equilibrium concentration. The other is going to give us a negative. So for example, if I use 2.33, well, 1 minus 2.33 is negative 1.33. That's a negative concentration. You can't have that. That means this value of X is no good. Okay, it's no good. So only the 0.93 is going to work. So again, 1 minus 0.93 is going to be 0.07. So that is good. So now we got 1 minus 0.93, which is 0.07, 2 minus 0.93, which is 1.07, and 2 times 0.93 is 1.9 molar. Okay, so there's a case where we had to use the quadratic formula. Any questions with that guy? So again, when you don't have to use the quadratic formula, don't use it. In fact, there's going to be quiz problems in next chapter when we do talk about when we could ignore certain values so that we don't have to solve the quadratic formula. If you can ignore the quadratic formula, you will be expected to ignore the quadratic formula. Okay, I will repeat that again and again later on as that becomes more relevant. But in this chapter, we can't ever ignore the quadratic formula. It just won't. It'll never work for the problems that we do here because the K values are not super small. So this says the equilibrium constant for the following reaction, so nitrogen reacting with hydrogen to form ammonia, the Haber process, has a K value of 9.6 at 300 degrees Celsius. We want to determine the equilibrium concentrations of the mixture, okay, that contains 1 mole of nitrogen and 3 moles of hydrogen in a 5-liter vessel at 300 degrees Celsius. So again, we know that we're going to be using an ice table. So anytime we're asked to calculate equilibrium concentrations, probably we're going to need an ice table. Okay, 90% of the time at least, we're going to need an ice table. So that means we're going to need the initial concentrations. So the initial concentration of the nitrogen is 1 mole of nitrogen in that 5-liter vessel. And so that's going to give us an initial concentration of 0.2 molar. And we need the initial concentration of the hydrogen, which we started off with 3 moles in that 5-liter vessel. And that'll give us an initial concentration of 0.6 molar. So now we have the initial concentrations of the nitrogen and hydrogen. We're going to set up our ice table. So we have the nitrogen plus the hydrogen in equilibrium with the ammonia. So we're going to have our initial, change, and equilibrium. So the initial told us the initial concentration of the nitrogen was 0.2 molar, and that of the hydrogen we figured was 0.6 molar. Again, we're always going to assume that we have a clean, empty reaction vessel to start with, so there'll be no products, unless, again, otherwise, you're told otherwise, okay? So our change, Keenan, what's my change going to be in nitrogen?
So you're going to be minus just X there.
Okay. Hydrogen?
And then minus 3X.
Yep. And the ammonia.
And then plus 2X.
Okay, so everybody gets that, right? We're always going to lose our reactants, so they're always going to be negative. We're always going to gain our products, so they're always going to be positive. We're always assuming the reaction's going from this reactants to products, okay? The signs will take care of it. Even if we know it's going the other way, we're going to treat it like it's going towards products, okay? So always minus for the reactants, plus for the products. And then we're just going to do it in terms of X, Y, or Z. And we're just going to use the coefficients. So that's a coefficient of 1, so minus 1x. That's a coefficient of 3, so minus 3x. And this is a coefficient of 2 and a product, so it's going to be plus 2x. Then at equilibrium, we just add them up. And that's always the true. Okay, we're just going to add the initial and the change to one another. And there are our equilibrium concentrations. So that's eventually what we're looking for, right, is those equilibrium concentrations, but we first need to determine X. So Michael, how am I going to determine X?
Quadratic formula.
Say again?
We use the quadratic formula.
Well, okay, how am I going to get to that stage? You're skipping a whole bunch of steps.
So I just plug everything into the KC equation. And
Okay, what is the KC equation?
it's going to be NH3 squared over N2 and then H2 cubed. And then you plug in the 0.2 minus X and in for the N2, the 0.6 minus 3X in for the H2, and the 2X in for the NH3 squared.
Okay,
And then
so
you just solve for X.
okay, but that we have X and K. We have 2 unknowns.
Where's the other unknown?
Okay.
Oh, I got you.
Is it unknown?
I mean, you could do a system of equations if you want,
But we would need multiple equations. This would only be one equation. Is this unknown?
I mean, we have the ones in. Yeah, never mind. I guess it's right there.
We know it, right? It was actually given to us. So you're right? So it's going to be 9.6 is equal to our equilibrium constant, which is going to be 2x squared. And then our concentration of the N2, which is 0.200 minus X. And then the concentration here of 0.60 minus 3x, and that is cubed. Okay, so you're saying we're going to have to solve this using the quadratic formula?
Well, I mean, there's multiple ways, but that's what I would do.
Okay,
I would just
that'll
fully
be
everything
the
out.
hard way, okay? Because this is actually going to be x to the third, and then that x times that is x to the fourth. Can't use the quadratic formula.
I mean, you could factor out the x cubed somewhere, x squared.
Right. So let's do this. So this then, I could actually rewrite this, right? I'm going to factor out a 3 out of this. Okay. Now it's got to be cubed when I take it out. So I'm factoring out a 3 cubed. So now this becomes, since I factored out a 3, well, 0.2 times 3 is 0.6. And then if I factor out a 3, well, 3 times 1 would be 3x. So that's just x. And this is still cubed. So I could continue to rewrite this then. Mine 0.2 minus x, 0.2 minus x to the first to the third, which means this is now to the fourth. Okay. Now what would I do next? Anybody, what would I do next? I got to get it to everything to at least squared, right? To use the quadratic formula.
Multiply the other side by 3 to the third, and then you can square root.
Okay, so actually that's what I'm going to do first, is I'm just going to take the square root of both sides. So I'm also going to move this over, right? So this is going to be 3 to the third times that. That's going to get rid of that. This value here is actually going to be equal to 259.2, and we have 2 sig figs. The 3 would be exact because we took it out. So now I'm going to take the square root of both sides, which again, you could do it this, or you could say it's raised to the 1/2. They mean the same thing, right? Okay, so the square root then of 259 is 16.099. So that's just this part of it here, right? That's just that. That then is now going to be equal. So if we're taking that, that's going to be 2x. And then we're simply going to get, that is going to be, right, 1/2 times 4 is 2. So that's going to be 0.2 minus x squared. So that's going to be 2x over, right? Then this portion of it, this really means this. So 0.2 times 0.2 is going to be 0.04. Then I have the 0.2 times negative x, so that's going to be 0.2x. Then I have this times this, which again is going to be negative 0.2x. Then I have negative x times negative x, which is going to be x squared. Okay, so that's going to be then 0.04. Then I have negative 0.2, so that's negative 0.4x plus x squared. Then I got to take each one of those, bring it over to the other side. I'm going to rearrange it when I do it. Oops, shit. I'm going to now multiply all this out. So then 16 times negative 0.4. Let's see. I get negatives. Oops, that's supposed to be negative. And that is going to be 6.4398x. And then 16 times the 0.004 is going to be plus 0.64398. Now, also, I want to subtract 2x from both sides as well. So I'm going to put minus 2x. Now this side equals 0. I now have to combine these two guys. So I'm going to have 16.099x squared minus, now this was 6 minus 2, so this is going to be 8.4398. And then this remains the same. Okay. Okay, any questions about that? Again, I can't stress anymore how important it is you guys do homework. Okay, especially if you're not strong in math, you need to do a ton of homework. Okay. Okay, so now we have it in the quadratic form, right? Now we're going to use the quadratic formula. So that's going to be x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. What is my value of a?
16.099.
What is my value of b?
Negative 8.4398.
Exactly. Again, remember it's negative 8.4398, and my value of c?
0.64398.
Yep. Okay. So you're going to plug it in once with a plus sign, once with a minus sign. Make sure this is all in parentheses when you put it into your calculator, and then divide it by 2a. Okay. That's going to give you two values of x. You're going to get a value of x equals 0.43155 molar, or x is equal to 0.09269 molar. Now, only one of these values is going to work. The other one is going to be bad. So which value is going to work and which one's going to be bad?
The one that's going to work is going to be the 0.09269.
Why won't this one work?
Because if you go back and plug that into the equilibrium concentration for N2, it's going to be 0.200 minus 0.4, which would be a negative number, and you can't have a negative concentration.
Can x be negative? So you're telling me that the concentration cannot be negative, and you are absolutely correct. Can x be negative, though?
I guess if it's negative, and then if you plug in the negative to a negative x, it would be positive.
So in this case, it couldn't be negative, right? Because that would give me a negative concentration.
Mm-hmm.
But if we didn't have zeros in here, if a negative x worked and none of the concentrations were going to end up being negative, all that means is that the reaction actually went from products back to reactants. So yes, we can have a negative x. Not in this problem, because that would give us a negative concentration. But in future problems, we will have negative x's. And it just means that the reaction is going from products back to reactants. Okay? So yeah, we got to eliminate this one because that's going to give us a negative concentration. So that means this is going to be our value of x. So now we can now answer the question, which was just what is the equilibrium concentrations? So this was 0.2 minus x, so minus our 0.09269 molar. And so that is going to give me a value then of 0.10731. This would have ended up being 23 sig figs. Again, I'll generally just ask you to give me to a certain number of sig figs, or on an exam, a reasonable number of sig figs in the written portion. For the Canvas portion of the quiz, which I will be posting an announcement right after class today, I was trying to finish writing the exam, and I got distracted because I realized I needed to check those submissions to make sure that all of you have figured out how to submit. You got to do that. Okay, you got to figure that out. Okay, so there's our N2. Then our concentration of H2, again, would be the 0.600 minus our 3x. So that's going to be 3 times our 0.09269 molar. Okay, and that would give us a value of 0.32193 molar, or 0.322 molar to the correct sig fig and rounding. And then finally, our ammonia is just equal to 2x and that then is going to be 0.18538 molar, or 0.158 molar. Okay, any questions about that?